Okay, so now for something completely different. We have to talk about, so the second part of the class, which will consist of 5 lectures, okay? And there will not be a final exam. This does not mean that you don't have to study, because I can change my mind. Okay? So it will be 5 lectures on probability. Okay? So probability theory. So we will try to cover probability theory a little bit. You should know most of the things. And then the law of large numbers, generating functions, how to compute moments, and so on and so forth. All things which will be important in statistical mechanics. Okay? They are also important for many other things. So I will mostly follow a book which I found sort of interesting. It's an old book which is called Probability Theory for Statistical Methods. Not necessarily. I think there is only one copy in the library, so if you want, I can lend you the book. That's the copy of the library. Not completely, but I think it has a good approach to it. So very practical. Probability theory can be actually made very theoretical if you talk about, I don't want to talk about it. Anyway, you can make it very, very mathematical. Okay? I don't want to do that because it's not the scope of our class. So what we want to do is to give you some ideas on how to compute the probability of occurrences of some events, and how this will be useful for our purposes of studying, of going from microscopic description to the macroscopic description. Okay, so the first and more difficult concept in the theory of probability is what is probability. Okay, so depending on how you define probability, you can find all sorts of paradoxes and so on and so forth. I will be very dismissive of those. And for me, probability, for us, the probability of a given event E is the number of occurrences divided by the total number of events. Sometimes we can count the total number of events. For example, if I want, I can count how many of you are there, and there are 15, okay? And I can count how many are guys and how many are girls. Okay, I think you are 8 and 7. Let me count the girls. Yes, okay? So the probability that somebody in this room is a guy is 8 divided by 15. The probability that somebody in this room is a girl is 7 divided by 15. Okay? In this case, I can count the total number of events, and which is the number of people in the room, and I can count the number of events, which I call event guy, event girl. Okay? There are, or for example, if I have a box and I have red balls and black balls, or white balls, black balls, I don't know, whatever colors you like, okay, 2 colors. I know the total number of balls in the box, and for example, I can count how many of them are red, how many of them are white. This is a situation in which I can completely count the total number of events and the number of events. But for example, there are other situations which this cannot be true. This cannot be done. For example, if I toss a coin, okay? I have a coin, toss it in the air, and I land it on my hand, and I see whether it's head or tail. Okay. So you know, a coin has two faces. On one there is somebody's head, usually, I don't know, like the queen, the king, the president of a republic, or some artist of your country, something, okay? And on the other end, there is, on the other side, there is something else, which is usually called the tail. Okay, okay, so I cannot count the total number of events because I can toss as many times the coin as I want. But still, I can talk about probability. So if a coin is fair, meaning that it's not been tampered with, it's symmetric with respect to its axis and so on and so forth. So when I throw it, I'm not able to throw it in such a way that to make it land always as I want. So it's a fair coin. It's called a fair coin. Then it's a perfect number generator, a perfect random number generator in some sense. And I can speak of the probability of having head or tail. And that if the coin is fair, the probabilities are equal. Okay? So in that case, you see, there is a slight difference between the two situations. In both cases, we talk about probability. I mean, there is no limit to the number of times I can toss a coin. And in that case, if I count the number of times that I get head divided by the total number of times, I will never get 1/2, exactly 1/2. In fact, what I get is an estimation of the probability. For example, if I toss a coin 200 times, and 103 times I get head, and 97 times I get tail, would you say that the coin is fair or not? You can have fluctuations. So you don't expect to have exactly 100 times. That's not a good random number generator. Okay, so in both, sometimes we encounter this, one of these probabilities, one of these concepts, one version of this concept of probability. Some other times we encounter the other version. Why is not? It is a perfect number. No, if you require that the number of heads and the number of tails is exactly equal, then it's not a random number generator, it's deterministic. If I have head, then the next one has to be tail. If I have tail, then the next one has to be head. And so that's not random at all. So if you want randomness, you have to allow for fluctuations. This does not mean that the coin is not fair. It's an inherent concept of in the probability. So for example, for a coin, I can have head or tail. These are two mutually exclusive events, right? If I have head, I don't have tail, and vice versa. If I have tail, I don't have head. But they cover completely the space of possibilities. I mean, we don't consider the situation in which a coin lands like this, and it's not either. Sometimes it can happen, in the movies, for example. So in the movies, it happens much more often than the probability theory will predict. So if we neglect this possibility, then the number of events in which we have, so number of events where we get the event E divided by total number of events. So number of events in which we get head plus the number of events in which we get tail divided by the total number of events should be 1. And this, in terms of probabilities, can be written like this. Probability of head plus probability of tail is equal to 1. If we have a series of events, EI, which are independent and mutually exclusive, then the sum of the probabilities of these events has to be 1.
Mutually exclusive?
Mutually exclusive means that if one happens, the other does not happen. Okay, like head or tail, or somebody wears glasses or somebody does not wear glasses. Either somebody has glasses or does not have glasses. It's no half glasses. If they are not mutually exclusive, okay, so the probability that you so the probability that we have event 1 or event 2 that we write with a plus so if they are mutually exclusive, this is just the sum of the two events. If they are not, that's not the sum. If they are not, if not, then there is a possibility that we have an event E1 and E2. For example, if I ask the probability that somebody is a guy and wear glasses, you can have either is a guy or that wears glasses. Okay? And the two things can occur together. They are not mutually exclusive. It's not that only that guys don't wear glasses. Okay? So this we define it as usual as the number of occurrences of event 1 and 2 divided by the total number of events. So the probability to have event 1 or event 2 is the probability that we have event 1 alone plus the probability that we have event 2 plus the probability that we have both. Okay? The probability that we have event 1 is equal to the probability that we have event 1 alone plus the probability that we have event 1 and event 2. And the same, the probability that we have event 2 is okay. So this equation is not valid anymore. What is the valid equation? You can check for yourself. It's quite easy. If they are not mutually exclusive, we have P of E1 plus P of E2 minus P of E1, E2. Because if we sum these two together, we get a 2 in front of N1, 2. Here we have only 1, so we have to subtract a term like this. Okay. So, have you seen these things before? Do you have a class on probability or as part of your math class, or maybe some of you are afraid of saying yes. Some of you say yes, some of you are afraid of saying yes. Okay. Don't worry, we have to cover it anyway, even if you already had it. Okay? It's always good to refresh. Okay, so let's make an example. Let's assume we have a fair coin, so the probability of having head is equal to 1/2, and the probability of having tail is equal to 1/2. Suppose we have two such coins, and we toss both of them at the same time, and we assume that the events are completely independent. Okay, that whether it's a head on coin 1 does not affect the result of the tossing of coin 2. Okay, so how many possible outcomes do we have of the experiment in which we toss two coins? Head, tail, let's say head 1, tail 1, head 1, head 2, tail 1, tail 2, tail 1, head 2. Okay, 4. Because I have two possibilities for coin 1, two possibilities for coin 2. 2 times 2 is 4. And the same, if I have n coins, I have 2 to the n possibilities. What is the probability that I have to associate to each of these events?
The probability of being head of coin 1 or
The product of the two probabilities, which is 1/4, right? Because each of these events occur with the probability 1/2, we assume they are independent. If they are independent, the probability of having E1 and E2 is equal to the probability of having E1 times the probability of having E2. Okay, so we have 1/4, 1/4, 1/4, 1/4. These are mutually exclusive events. What? Oh, sorry. No, it's this one that I got it wrong. Sorry. Okay, sorry. My mistake. Yes, with the it's this one that I got it. So this means head on the first and tail on the second. Of course, every configuration has to have a 1 and 2. It can have 2 H or 2 T's, but it has to be a 1 and a 2. Thanks. Sorry. These are mutually exclusive events, and they cover all the possible outcomes of the experiment of tossing 2 coins. So whether they are independent or not, their probabilities have to sum to 1. If they are independent, we can check explicitly that they sum to 1, putting in the numbers because we know. But even if they are not independent, even if I say something like this is 1/4, instead of having 1/4 and 1/4, I say something like, 1/5, and what sums to 1/2? No, say 1/6 and 2/6. Okay? If I change this, then it means that the 2 events are not independent anymore, because they do not satisfy this equation. But they still the sum of the events, the probabilities of the events have to sum to 1. Okay? So this means that coin 2 knows whether coin 1. In this situation, coin 2 knows, quote unquote, what's happening to coin 1. Because if coin 1 has head, then coin 2 is more likely to have head than tail. If coin 1 gets tail, then coin 2 is independent. Okay, let's go back to the. So what is the probabilities of having 2 heads here? 1? 1? 1? 1 over 2. 1 demi, you said. Okay. It was half English, half French. So the probability of having 2 heads is 1 over 4. The probability of having 2 tails is the probability of having 1 tail and one head is 1 over 2. Why? Because we have 2 possible configurations that have 1 head and 1 tail. Okay? So the probabilities of having 2 t's is equal to 1/4. The probability of having 1 t and 1/8 equal to 1/2. Because since we have not specified which coin has to have tail, which coin has to have head, we have to consider both configurations. Let's consider a die. So have you ever seen a die? Yeah. This was a rhetorical question. So what's the property of a die? That opposite faces opposite faces sum to 7. Did you know this? So the opposite faces sum to 7. Like if you have a 1 here, it means you have 6 on the other side. If you have 3 here, it means you have 4 on the other side. And then 5 is opposite to that. Do you know how many ways are there to make dies? If I assume that they have to sum to 7, that the opposite faces sum to 7, you know how many possible ways I can actually build the die? It's not 36 because apart that it would not be 36, but it's not a very big number because I can rotate the die and it doesn't matter. Okay. There are only 2 ways of doing a die. Okay. Either it's like this or it's like this. So either there is no way you can rotate this to match this. And these are the only two possible configurations. You believe it? If not, you have to try yourself. You try to construct a die that has the property that the opposite faces sum to 7, okay? And try to build it in a different way like this, of this. You can't. There are only two possible ways. you can say this die is counterclockwise, this die is clockwise. Because you do 1, 2, 3 by looking in the opposite direction of the clock, and the opposite direction of how the clock moves, or like this. Anyway, you can have fun. Have you ever played these games? Like they were big in the when I was a kid in the 90s, in the early 90s. These games where you have these very complicated dice that have 20 faces, 25. Have you ever seen these things? Like there are these games in which like somebody's a sorcerer, somebody's an elf, somebody's role games. They're called. Okay, then you have to you play with dice which are very complicated. They're like 12 faces, 24 faces, and they also have to respect some rules, like the sum of the opposite faces have to sum to something if they are opposite. Okay. Anyway, so let's consider a die. Doesn't matter which of the two families of dice. Okay, so the probability of having one of the numbers. Let's assume that the die is like the coin. It's fair. Fair means that when I throw the die, I see the uppermost face, and with equal probability, I get one of the 6 numbers. So therefore, there are the probability of getting any number, like the probability of getting 1, is 1/6. The probability of getting 2 is 1/6. Okay? Now, the probability of, now we throw 2 dice. The plural of die is dice. So it's not 2 different things. I say die and dice. I throw 2 dice. Okay? And what's the probability that I get on the first die 2 and on the second die 3? The probability of getting 2 and 3. 1/36. For this problem that I said, they can be differentiated. One is blue and one is red. Okay. Then what is the probability that I get 2 on the red and 3 on the blue? Is 1/36. Now let's erase the colors. What's the probability that I get a 2 and a 3? 1/18. 2 and 3. So let me write like this. That I get the set 2 and 3 is 2 divided by 36. Because I can get 2 on the first or on the second, so I have 2 possible configurations, 1/18. It's important that we ask this kind of question as your friend has asked, because we have to ask whether the particles, the dice, the coin, are distinguishable or indistinguishable. If they are distinguishable or indistinguishable, we get different countings. Okay? So, what's the probability? What is the probability that I throw 2 dice and the sum of the 2 numbers is 5? That the sum of the 2 numbers is 5. what should I do to compute this thing? Like, for example, if I get a 2 or a 3, a 2 and a 3, that's the sum is 5. But how can I get the probability that the sum is 5? I accept also answers in French. What should I do? List all the possibilities. What are all the possibilities? Let's list them here. 1, 4, 2, 3, 3, 2, 4, 1. Each of these has probability 1 over 36. There are 4 of them. So 1, 2, 3, 4 is 4 over 36, which is 1/9. Now, what's the probability that the sum is 2? One over 36. Okay.
In this case, they are distinguishable.
In this case, no, they're not. It doesn't matter. I'm asking about the sum. So I'm only looking at the sum of the numbers. Doesn't matter if it's on the red or on the blue. So I'm not looking at the color of the die. What's the probability that they sum to 6? I have to list down all the possibilities. Do you expect it's larger or smaller than this? Which is slightly larger than 4 over 36. Okay? So now, just for you to check, just try, all possible. What's the maximum number you can get? 12. As an exercise for you, try the probability of calculate the probability of getting a number from 2, which is the minimum, to 12, which is the maximum. Sum them, and you have to get 1. Okay, because you have to get one number between 2 and 12. So they are mutually exclusive events. Okay, so much for our die. Let's go back to the coin. So if I throw n times a coin, a fair coin, or I throw n coins at the same time, doesn't matter. Okay? If they are independent, if the events are independent and the coin is fair, then the two things are equivalent. And I ask, what's the probability of getting k heads and n minus k tails? Well, first of all, I said that the coin is fair, so I get 1/2 to the k, and then 1/2 to the n minus k. But then I'm asking only of the total number of heads and the total number of tails. And not asking the first coin has to be head, the second coin has to be tail. Yeah. Okay? So there are many configurations which are equivalent. For example, a configuration like this, head, tail, tail, head, for n equal 4, is equivalent to this configuration, tail, head, tail, head. I have to count the number of equivalent configurations. I'm sure you have seen this before, so you know the answer. What's the answer? D? Say, I just didn't understand what you said.
K to the power of k.
No. The answer is the binomial coefficient. Okay? The number of configurations. So why is the binomial? Let's try to see. Okay? So first of all, I can permute all the objects. Okay, I have 4 objects. I can permute it in as many in as many ways as I can, and the result will not change because I'm only asking how many heads are there, how many tails are there. So if I have 4 objects, how many ways of permuting? How many possible permutations do I have? 4 factorial. 4 factorial, which is 24. Is it 24? It's 4 times 3 times 2 times 1. 24. So the total number of possible permutation is 24. Why? Because I can choose the first object as I wish. I take it. I decided it. Then I'm left with n minus 1 object. And I decide the second object, the position of the second object, and so on and so forth. So I have n times n minus 1 times n minus 2 times n blah, 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 until I cannot do that anymore. So the total number of configurations is 4 factorial. But not all the configurations, when I permute these objects, not all the configuration will be, will change, will be really a new configuration. For example, if I exchange these 2 heads here, I'm not getting a new configuration. So I have to divide this 4 factorial by the number of ways I can permute the objects with the given property. For example, I can permute the objects which are only head. How many times I can, in how many ways I can do it here? 2 factorial. And the same with the tail. So I get another 2 factorial. But that 2 factorial, let me write it as 4 minus 2. Because if I have n objects and 2 are heads, then the other 2. So with general n and k, this becomes n factorial divided by k factorial n minus k factorial. So each of these configurations has this probability, 1/2 to the k, 1/2 to the n minus k. By the way, since this is 1/2 and 1/2, I could have just written 1/2 to the n. I'm just writing 1/2 and 1/2 minus k because if the coin is not fair, and this is p and this is q, small p and that is small q, then here I have to write p to the k, q to the n minus k, which is not p to the n or q to the n, if p and q. And so the number of configurations, let's get back, is n factorial divided by k factorial n minus k factorial. Okay? So this is the probability that we have k heads k heads out of n tosses. Tosses of a coin. I tossed the coin. Let's see if it satisfies the. So, if I first of all, is it clear? So there are two steps in computing the probability of an event, a complex event happening. First of all, you have to compute the probability of one simple event happening, and then you have to count how many of these simple events correspond to this complex event. The simple event here is the sequence, HT, TH, blah, blah, blah. The complex, quote-unquote, event is how many heads are there, how many tails are there. Okay, are there k tails? So I have to merge these events into a single event. So the probability of the single event increases. So first of all, the probability of having 2 tails out of 10 tosses or 3 tails out of 10 tosses, are they, these 2 events, are they mutually exclusive or not? What do you think? I'm asking the event, let's call it E2, is the event in which I have 2 tails out of 10 tosses. And the event E4, let's say, in which I have 4 tails out of 10 tosses. I am asking, are they mutually exclusive or not? What does it mean, mutually exclusive?
That one event depends on the other.
No, I'm not saying independent. That's independent. I'm saying mutually exclusive. They cannot happen together. If one happens, the other does not happen. Either I wear glasses or I don't wear glasses. Hmm? They're not mutually exclusive. Why? No. I'm asking not if I have at least 2 tails. I'm asking if I have exactly 2 tails. Hmm? You did not understand? So, for example, one configuration in which I have 2 tails out of 10 tosses. H, H, T, T, H, 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 H. One configuration in which I have 4 tails out of 10 tosses is H, T, H, T, 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 5, 6, 7, 8, 9, and 10. Can you have one and not the other? I mean, can you have one and the other at the same time? Can you permute these tails in such a way that you get one of them? No. They are mutually exclusive then. I'm not asking, the question was not at least 2 tails. In that case, they will not be mutually exclusive. Because if I have 4 tails, then I have at least 2 tails. Not vice versa, though. Okay. But here I'm asking, if I have exactly 2 tails, this is the event E2, and the event E4 is if I have exactly 4 tails. So they are mutually exclusive. All the events EK, for k that goes from 0 to n, they are mutually exclusive. And therefore, the sum of their probabilities and not only they are mutually exclusive, but they are the only possibilities also that you have. Because any configuration will have a given number of heads, which is between 0 and 10, and sorry, the number of tails, which is 0 and 10, and it's uniquely defined by that event. So it covers all the space of the possibilities. So they are mutually exclusive, and they cover the entire space of possibilities. So this sum has to be equal to 1. Yes.
Mutual exclusive. I think maybe I'm confused. If in French, in fact, I think it's like this also. The first one, you can find some elements who are in the second.
So you can find some elements of this ensemble which are, for example, give me an example.
When you have E1 and just saw E2, there is some elements. So when
Yes, which one? Give me an example.
there, okay, let me take.
So the element of the first set have only 2 tails, and exactly 2 tails. The element of the second set have only 4 tails, and exactly 4 tails. So which elements are in common?
So then just cycle 0, A1 and A2.
Yes, the intersect is the empty set.
Probability will be called probability of first one plus the probability for the second one, because A1, A2 equals 0. Mutual where there is not.
Mutually exclude. To exclude somebody means to push it away. Okay? To exclude somebody from, I can exclude you from the class, I can take you and send you out of the door, and then I have excluded you from the class. Mutually exclusive means that you can also exclude me. You can take me and you can send me out of the door. And mutually exclusive means that if one exists, then the other does not exist. If one happens, then the other does not happen. It's like when I come to class, you don't come to class, and vice versa. When you come to class, I don't come to class. Okay? Okay? So there is no intersection in the events in which you are in class and I am in class. Okay, so this means that if I sum for k that goes from 0 to n, 1/2 to the k, 1/2 to the n minus k, n factorial divided by k factorial n minus k factorial, I should get 1. Have you ever seen this identity before? This is when you have something like a plus b to the n. How can you expand it? With the binomial expansion. So this becomes k 0 to n, a to the k, b to the n minus k, and then n factorial divided by k factorial n minus k factorial. So this is equal to 1/2 plus 1/2 to which power? To n. So this is 1 to the n, which is 1. And as you see, this does not depend on the fact that we chose 1/2 and 1/2. We could have chosen p and q as far as p plus q sums to 1. Okay? So this identity here is very powerful and also very important. Essentially, probably the most important identity in probability theory. There are many interesting theorems one can prove with very complicated identities, but this one is used. So it's one of the building blocks of probability theory. So since it's something that we will encounter later on, let me tell you also the following. So suppose this is the binomial coefficient. There are also multinomial coefficients, okay? And they count the following things. So suppose, for example, let's make the example with three objects, not head or tails. Let's call them, I don't know, A, B, C. A, B, and C. And I can make strings of A, B, C. A, B, B, C, A, B, B, A, okay? Or B, A, C, B, B, A, B. And so on and so forth. I make random strings of 3 letters. And I'm asking, then how many strings have of length n have n A A's, and B B's, and clearly n C, which is n minus n A minus n B C's. I want to count the number of strings of length n which have n A A's, and B B's, and C C's. How can I count this? I could reason like as before, right? What did we do with the binomial coefficient? What is the total number of permutations? So I have a string. I'm only counting the total number. Again, I'm only counting the total number of occurrences of A, of B, and C. So I have this string as the generating string in some sense. So I have this string, and I can generate all the other strings by permuting the objects of this string. How many permutations do I have? N factorial. But not all the strings that I generate in this way will be new strings. Why? Yes, so I can pick, I have the possibility of picking 2 A's and permuting them and not changing the string. Or 2 B's and permuting them and not changing the string. 2 C's and permuting them, not changing the string. So out of this configuration, NA factorial, NB factorial, and C factorial. And C, I can write it as N minus NA. Let me write NC factorial, and then that identity holds. And so on and so forth. If I have 4 possibilities, then I have to divide N factorial by NA, N factorial, NB factorial, NC factorial, and D factorial. This will be useful in statistical mechanics later. Okay, so the last thing that I want to do, I have to take 10 minutes. Okay, So, the relative probability. Probability of an event E2 given an event E1 has happened. Probability of E2 in the subset of instances in which E1 happens. Okay? For example, I can ask the probability that that somebody wears glasses in this class and he is also a guy, not a girl. Okay? So let's make an example. So there are 8 guys out of you, and only him is wearing glasses. Okay? So the probability that wears glasses, given that the guy, is what? 1 over 8. Okay? 2. Oh, shit. Oh, you take them. You're like her, because she wears, sometimes you wear glasses, sometimes not. So it's difficult. So you see, these things fluctuate. Okay. Doesn't matter. We can, the algebra should work the same. Okay. So now the probability that somebody wears glasses and it's a girl is okay, there are 7 girls and she's not wearing glasses. Only her is wearing glasses. So only she is wearing glasses. So it's 1 over 7. Okay. Actually, let me correct for him. Okay, 2 over 8. Okay. So if I want to get the probability that somebody wears glasses, and I don't care whether it's he or a she, what should I do? I have to add them, but I have to multiply them by something. By pi, I don't know. By Avogadro's number. No, I have to multiply them by the probability that a random person is a guy or is a girl. Okay? So I have the probability to wear glasses is 2 over 8 times the probability that somebody randomly picked from the class is a guy, which is 8 over 15 plus 1/7 times what? 7 over 15. So if you do the math, you find that this is 3 over 15. And this works because we have 3 students with the glasses and the teacher is excluded. Okay? Okay, so the probability of an event A can be written as the probability of an event A given that E1 has happened times the probability of E1 plus the probability of the event A given that E2 has happened times the probability of E2 and so on and so forth. Okay? So let me write this as a sum over I of P event A, EI. Okay, let me stop here and we'll continue tomorrow.